This is Jack Jackson with part 11 of our series of probability lectures. This is on discrete distribution parameters. So what we're going to be doing here is we're going to be taking discrete distributions and seeing how we can describe certain characteristics of that distribution. So just as we use descriptive statistics to describe interesting characteristics of a set of data that may have been from a sample or may have been a population, we can think of a probability distribution as representing a population. And then we can describe the distribution with most of the same parameters that we studied in the unit on descriptive statistics. For example, we can describe the center of the distribution by identifying the mean, median, and mode of a distribution. And we can identify the variability of a distribution by identifying its standard deviation or variance and so forth. We can talk about skewness and so forth. So all the different kinds of things that we talked about in describing a population with parameters. Remember that if we described a sample, it was called a statistic. When we describe a population, it's called a parameter. We also have parameters which describe a distribution. So basically you can think of it just like a population. So for example, to get us started here, suppose we've got a sample here, or a population. Let's suppose it's actually a population. And here's a frequency table for this population. We have 5 2s, 4 3s, 2 5s, and 5 11s. So if we want to compute the mean, we have to add those up. That's 2 plus 2 plus 2 plus 2 plus 2, 5 2s, and then 4 3s, 2 5s, and 5 11s added together. Now, of course, there's a shortcut to this. Since we've got the same number added together over and over again, what's the shortcut to that? Yeah, it's multiplication, of course. And so we can rewrite that as 2 times 5 plus 3 times 4 plus 5 times 2 plus 11 times 5. So in other words, what are we doing? We're taking the data value times its frequency and adding all those up and then adding up the total of all the frequencies, which is 16, and that's the total n that we're dividing by. And so in this case, that turns out to be 87/16 or 5.4375. Now I want to look at this a slightly different way, however. What if we take this 16 here in this fraction? So we got 2 times 5 plus 3 times 4 plus 5 times 2 plus 11 times 5 over 16, and we want to distribute that over each term. And in fact, we're going to write it under the part that's in parentheses. So now we have 2 times 5/16 plus 3 times 4/16 plus 5 times 2/16 plus 11 times 5/16, and that's the same thing. Well, what are those numbers in parentheses now? Well, they're just the relative frequencies. But notice that's also basically the same thing as saying they're probabilities. The probability, if we took these 16 numbers and wrote them down on pieces of paper, on 16 different pieces of paper, put them in an urn or a hat or something and shake them up and randomly pull out one, what's the probability that we'll pull out a 2? Well, that should be 5/16. Or what if the probability of a 3? That would be 4/16. So to find the mean, one way we could find the mean is take each x value, each data value, times its probability, assuming the probability of just drawing that particular data value, choosing that one at random out of all of the data values. So we're taking each value of x times the probability. Well, this is going to lead us to how we find the mean of a sample, of a distribution. So the mean of a distribution is also called the expected value of x, with this e bracket x here. And what we do is we're going to take all the x's times the probability of those x values, and we add all those up where x goes over all possible x's that are in the domain of this distribution function, all possible values of the random variable. So here's another example. Now think of this as a random variable x, and we start with this table 4, 6, 8, and 11 for the x's, and we have the probabilities of each one, 0.2, 0.3, 0.1, and 0.4. And of course, if it's a probability distribution function, these probabilities must sum to 1. If they don't, you don't have a distribution. Something's wrong there. Okay, but they do add up here, so this is a legitimate distribution, a finite distribution. And so what we do is we take each of these x values times the probabilities. So we take 4 times 0.2 to get the 0.8, 6 times 0.3 to get 1.8, 8 times the 1/10 to get 8/10, and 11 times 0.4 gives us 4.4. And then we add up those values in the last column to get the total of 7.8, and that is the mean of the distribution. Again, you can think of this the same way as we would if this was a data set where we know that 20% of the data is a 4, 30% of the data is a 6, 10% is an 8, and 40% is an 11. Mix those all together and randomly draw out one. What's the one item? What's the probability that it's a 4? Well, that is 0.2. Probability that it's a 6 is 0.3, and so forth. So we work this out just like we did the last example here, where we're multiplying by these relative frequencies, which are just the probabilities. And so that's why we get this. Now, this idea of an expected value of x, another way to think of that is it's what we would expect to happen on average. It's the mean, after all, is the average. So on average, we would expect to get about a 7.8 if we were to do several of these and average them. Now, we also use the same letter we use for the mean of a population, the lowercase Greek letter mu. Now, in general, we can find the expected value of any function of a random variable x by the formula. The expected value of this function of x is you take that function of x, g of x that is, times the probability of x, and then add those up over all x's in the domain of your probability density function here. And of course, this p here is the PDF, the probability density function. So of course, if g of x is just the function g of x equals x, then this is just the expected value of x, which is the mean. And of course, the mean is going to measure the center of the distribution. We could also talk about the mode of a discrete distribution. It's the value of the random variable with the highest probability. On a graph, it's the x value with the highest bar. So you can see it in the table here on this particular example, where 0.4 is the biggest value for probability, so 11 is the mode. Or you can look at it over here on the bar graph, which is the graph of the PDF, and we see the highest bar is the one at 11, so 11 is the mode. I don't have too many notes on it here, but sometimes you can find a median of a distribution as well. A median of a distribution is a data value so that 50% of the data is below that. Or in other words, where the cumulative probability is 50%. And actually in this case, 6 would be the mode, because notice that exactly 50% of the data is at or below 6 here. So 6 is the median in this case. The mode is 11, and the median is 6. Sometimes it's hard to find in a discrete case like this a single value that will be exactly at the mode, at the mode or the median. You put one in here, and so oftentimes by the time you do the CDF, the cumulative density up to that point, it's already above 0.5 or it's below 0.5. You can't get one exactly on. So then you have to extrapolate somehow, or interpolate actually. And similarly for the mode, it's possible for the mode not to exist because we could have ties. And the same kind of decisions we made about data, I think in this class we decided if there was a tie for 2, we would still call it bimodal, but above that we would just say it didn't have a mode. Now what about the variance? Well, a variance is the expected value of x minus mu squared. Now if you'll think about how we computed variance back for a population, this is exactly what we did. We took the x, we did the probability of x times x minus x bar squared, add those up. Well, we did it a slightly different way. Instead of the probability here, we had we added up all these squares here, but we divided by the number that we have, and that basically boils down to be basically the same thing as multiplying by these probabilities each time. Okay, because remember, this is a relative frequency for each x, and again, it shows up multiple times in that sum. If you think of this probability as being a fraction, the top number is a weighted average on this because it counts how many times that x shows up, and we're dividing by the n at the end. We can distribute that in, it becomes a probability there. So basically this is the same setup as with the average, but this is also the same by putting the probability in here, but it's also the same as the way we did standard deviation before if we'd done this from a frequency, relative frequency table or a frequency table. And of course we use exactly the same symbol that we used for the variance of a population, sigma squared. In fact, we want to really think of a probability distribution as basically being a population, at least a theoretical description of a population. So notice again, this is our use of our general expected value thing. The expected value of something is that something times the probability of x, and then add them all up over all the possible x's. And the something we're looking at are squared deviations from the mean. Same idea that we had back when we did variance before. So let's actually compute this for a finite distribution. So here we have a finite distribution. The x values are 4, 6, 8, and 11, and the probabilities are 0.2, 0.3, 0.1, and 0.4. I believe this is the same distribution we were looking at earlier. Let's take a look here. Yeah, same distribution. Here's the table. Here's the graph for it. Okay, so the first thing we want to do is figure out the mean. Okay, so to figure out the mean, we're going to first figure out the x's times the probability of the x's. And here they are in this table. 4 times 0.2 is 0.8, 6 times 0.3 is 1.8, 8 times 0.1 is 0.8, and 11 times 0.4 is 4.4. And we add those up, we get 7.8. That is the mean. That is the mu up here in the formula, and that is our mean. Now what we want to do is we want to find all the x's minus the means, the deviations from the mean, so x minus mu. So what we're doing is we're subtracting the 7.8, so that is, go the x, 0.2 minus 7.8 is minus 3.8. So that x value of 4 is, x minus mu, not the probability. 4 minus 7.8, that's negative 3.8. So the 4, the x value is 3.8 below the mean. Do the same thing for the 6. 6 minus 7.8, that's negative 1.8. So 6 is 1.8 units below the mean. Then we do 8 minus 7.8, that's positive 0.2. So 8 is 2 units above the mean. And 11 minus 7.8 is 3.2. So that's 3.2 units above the mean for the 11. So notice each time we were subtracting this mean of 7.8, the one with the purple background there. Okay, so now we have all the x's minus mu. The next step is to square all those. So here we go. Negative 3.8 squared is 14.44. Negative 1.8 squared is 3.24. 0.2 squared is 0.04. And 3.2 squared is 10.4. Now we want to multiply each one of those by the probabilities. So we're going to take the 0.2 times the 14.44 to get what goes in this last blank over here onto the right. And that is 2.888. Then we take the 0.3 times the 3.24 to get the 0.972. We take 0.1 times 0.04 to get 0.004. And 0.4, the probability of 11, times x minus mu squared of 10.24 gives us 4.096. So all these values in this last column are x minus the mu squares, then times the probability of the x's. And that's the things that we want in our sum here for the answer, so we just add those up and get the number with the pink background. So 2.888 plus 0.972 plus 0.004 plus 4.096 gives you 7.96, and that is the variance. That's the expected value of x minus mu squared, or the sum of x minus mu squared times the probability of x's, and this goes directly by the definition. So next I want to look at this formula just a little bit more, and let's do a little bit of algebraic manipulation here. So we're going to manipulate some symbols around, do a little algebra. So sigma squared, that is the variance, is the expected value of x minus mu squared. So by definition, that is the sum over all x's in the domain, all possible values of the random variable x. We sum x minus mu squared times the probability of x, as we just saw in the table. But I want to do a little algebra here. So look at this x minus mu squared, we square that. Notice you square the first term, you get x squared. Square the last term, that's plus mu squared. But you also get a middle term of minus 2 x times mu. If you want to think of that as using the distributive property, sometimes referred by the anagram FOIL, you can FOIL this out, that is distribute it out. As you multiply it by itself, you're going to get this. Don't forget you do get that middle term there. Now I'm going to take the p of x and distribute times each one. And so that gives you x squared times p of x minus 2x mu times p of x plus mu squared times p of x. Well, now I can break this sum into 3 parts. I can do the sum of the first part, the sum of the next part, and the sum of the next part. So what I'm really using there is a combination of the commutative and associative properties of addition to rewrite those. Now let's see what else I can do. The middle one here, if things that do not have an x in them can be brought out, factored out front, so I'm using the distributive property factoring there, so I can factor out the negative 2 and the mu. And the last one I can factor out the mu square. So this gives me this expression at the bottom here, the sum of the x squared times p of x minus 2 mu times the sum of the x times p of x plus mu squared times the sum of the p of x. Let's start on the far right. What is the sum of p of x over all the x's in the domain? You should know the answer to that. Think about that a minute. What is this sum right here? Well, it's 1, of course, right? If we add up all the probabilities, they turn out to be 1. And so this expression at the end is just 1. So then the last term is just mu squared times 1, or mu squared. Now what about this sum right here in the middle term? The sum of x times p of x? Do you recognize that? What is that? That's the expected value of x. That's the mean. So that's just mu. So I can replace this middle sum by mu and the last sum by 1. Now the two mu's multiply together to give you mu squared. Of course, 1 times mu squared is mu squared. So I got negative 2 mu squared plus mu squared is negative 1 mu squared. And so what we have is the sum of x, all x's in the domain, of x squared times p of x, which is just the expected value of x squared, minus the mu squared, which is the expected value of x, quantity squared. So an alternative formula for figuring the variance is the expected value of x squared minus the expected value of x, quantity squared, or the sum of x squared times p of x minus mu squared. So let's do the same table that we did a while back. Let's do that, but the same table making a PDF. Let's figure out the variance using the alternative formula. So it maybe makes some sense out of this as we put it into action. So we start with our x's and our p of x's. And of course, once again, we find our mean, same as before. But now we're going to find out x squared times p of x. So we're going to take all the x's and square them. So 4 squared is 16, 6 squared is 36, 8 squared is 64, 11 squared is 121. And we want to add those up, or we can add those up if we want. We don't actually need that number though. Then we want to take each x squared times the probability. So 0.2 times 16 is 3.2. 0.3 is the probability of 6 times 6 squared. 0.3 times 36 is 10.8. 0.1 times 64 is 6.4. And 0.4 times 121 is 48.4. So these four numbers are the x squared times the p of x's, and we want to add all those up to get 68.8, and that's the expected value of x squared. The 7.8 is the expected value of x. So to find the variance, we take this expected value of x squared, that is the 68.8, and subtract from that the square of the mean. So what we do here, try it out on your calculator if you want. 68.8 minus 7.8 squared. Let me say it again. 68.8 minus 7.8 squared, and you should get 7.96, which is exactly what we got with the other formula. So if we use this middle formula here, that's the actual definition of variance, but we can also use this alternative formula. Take your pick, whichever one is easier for you to use. The one in the middle, I think, makes a little bit more sense in terms of what it is actually measuring, because again, remember when we talked about this before in the descriptive statistics chapter, we're talking about deviations from the mean, squaring those things, multiplying it by probabilities, and then that gives us the and adding them up, that gives us the variance, a measure of variability. When I say multiply by the probabilities, all we're really doing is we're just averaging them. When we add them, when we're multiplying by the probabilities, adding them up, we're averaging. What the probability does, it allows us to weight that average. So if we have repeats of a certain one, or more weight to that average, that's what the probability does. That one I think explains a little bit more about what the variance really is and why it is a measure of variability. However, this last formula sometimes is a little easier to compute, especially the days when they did this without computers. They definitely would have used this last example to do some computation. Okay, so let's continue on here. So of course, in either case, whichever version you use to find the variance, just take the square root to get the standard deviation, and of course we use sigma again for the standard deviation and sigma square for the variance. So again, the standard deviation is the square root of the variance, just like it was in descriptive statistics, and so the standard deviation is probably our best and most often used measure of variability when we're dealing with distributions. Now, let me briefly talk about the skewness of a discrete distribution. Remember, we talked about the skewness of a data set. We said that it's a measure of deviation from symmetry. So if a data set is perfectly symmetric, then the skewness is exactly 0. And a positively skewed data set is also said to be skewed to the right, and it'll be more spread out on the right side, so it'll have more of a tail out to the right side than it does out to the left. More spread out on the right side. Of course, the opposite's true if you have a negatively skewed, or has a negative skewness. It'll be skewed to the left, and the tail will go to the right. So it'll be sort of more bunched up on the right, and the tail out to the left if it's skewed to the left, and that's a negative skewness. Now, when we talk about this, there's actually a number you can compute for skewness. What you do is you basically take a z-score. Remember how we did a z-score? You took the x minus the mu and divided by sigma, and then you cube that and find the expected value of that. So in other words, you take x minus mu, divide by sigma, and cube it, multiply by the probability of x, and add those up. Now, what this does, notice that an odd power there, since it has an odd power, if things are balanced on both sides, perfectly symmetric, you're going to get just as much of a negatives added into this sum as you're going to have the balancing on the other side is going to contribute positively to this sum. And those parts are going to cancel out, and you're going to end up with a skewness of 0. Okay, you do not have to know this particular formula. Since we're talking about skewness, I thought I'd throw it in so that so that you have it there for reference and you'll understand maybe a little bit about it. But I will not ask you any questions dealing with this formula. What I may ask you questions about is something dealing with just looking at a distribution and telling whether it's skewed to the left or right. But just know that there is some formula there, and it is another application of the more general idea of expected value of a function. So that gives us several different characteristics, several different parameters that we might look at for a distribution.